notes that we started on Friday. But if you're Gold Day and listening to this, right, you would have done the notes yesterday or Monday. Anyway, here we go. We did the unit circle, right? And we came up with, using Pythagoras, cosine squared theta plus sine squared theta equals 1. I call this identity the big one. Okay, because wherever, and it's an identity because wherever you see cosine squared theta plus sine squared theta, you can replace that with a 1. So this is the Pythagorean identity. It's the very first one. Okay? And how did we come up with it? Obviously we used Pythagoras, right? We went cosine squared plus sine squared has to equal the hypotenuse squared. Right? Now, somebody in another class asked, well, Mrs. Muller, what do you do if the radius is not 1? Will that still hold true? Well, let's see. Shall we draw a circle where the radius is not 1? All right. So let's do that. Here we go. Here's my circle, and I'm actually making it smaller than the one up here. But I'm going to call it R instead of 1. And I'm going to have an angle here, theta. And what would this point be? Instead of cosine theta sine theta, that point's going to be, good, R cosine theta, R sine theta. And so if I were to drop a perpendicular here, what is the distance here on the x-axis going to be? R cosine theta, yep. And the distance on the y-axis would be R sine theta. So may we set up another Pythagorean relationship here with this triangle? What would it be? It would be R cosine theta squared, right, plus R sine theta squared equals R squared. And so we could then break this up a little bit and say, well, that's just going to be R squared cosine squared theta plus R squared sine squared theta equals R squared. And then what could we do? Take the R squared out, and we get R squared times cosine squared theta plus sine squared theta equals R squared. Divide by R squared. And so what happens is these cancel, and we're left again with cosine squared theta plus sine squared theta equals 1. So guess what? Does it matter what circle you're on? No. Yes, sir, John.
You're not, when you do R cosine theta squared, when you write it like that, you're not squaring the theta, are you?
No. No.
Yeah.
No, convention is when you're doing a trig function that's squared like this, convention is you would write this as sine with the sin, and the square goes here. That means you're squaring the entire ratio.
Yeah.
Okay? If you had something like this, that's different. That's different. Okay? So this is different. And I believe that's why they came up with the convention and put the square inside between here, so you would know you're not squaring the x. That's a great question. All right, so anybody got any questions? So it doesn't matter what the radius is, because the radius itself will divide away. All right, so let's take and put that information under Pythagorean identities here, right? The big one is going to be under here, and they want it for values of x. So instead of theta, I'm going to use x. So this would be cosine squared x plus sine squared x equals 1. or theta, right? Because it's representative of an angle regardless of whether we use an x or a theta. Okay? So you notice there are two more spots to fill up here in this Pythagorean identity. So what are we going to do? We're going to go back to our big one, and let's say we took this big one and took the big one and we divide, whoops, it helps if I have a marker. Dividing the big one by, let's say we go wild and crazy and say we're going to divide it by cosine squared. Cosine squared theta. So we'll take the big equation here, the big one, and we'll say cosine squared theta plus sine squared theta equals 1, and we're going to divide it by cosine squared theta. So what happens when we do that? What do we get? What is our result? Well, what's cosine squared over cosine squared? 1. Very nice. Whoops. 1 plus sine squared. That's tangent squared. Yes, very nice. Tangent squared theta equals, it's secant squared theta. Very nice. So this one is the second Pythagorean identity. So we're going to go to the next page, or your previous page, and you're going to write 1 plus tangent squared x equals secant squared x. All right, so what do you think is going to happen now? What are we going to do with the big one? That's right, so we can now dividing the big one. God bless you. By sine squared theta. So we'll take the big one, which is cosine squared theta plus sine squared theta equals 1, and we'll divide everything by now sine squared theta. So what happens when we do that? Good. Cotangent squared theta plus 1 equals cosecant squared theta. Everybody follow that? So this is the third Pythagorean identity, so we can take this and put it on the other page. And that's going to be cotangent squared x plus 1 equals cosecant squared x. So we have three Pythagorean identities, all derived from the big one, which is cosine squared theta plus sine squared theta equals 1. Now, you'll notice on the left here I have reserved something called the Pythagorean identities. I mean, not the reciprocal identities, right? So, that means I can multiply two of the trig functions together and get 1. Right? So can you think of two that are reciprocals of each other that if you were to multiply them together you get 1? Okay, so you could say sine x times cosecant x, because they're reciprocals of each other, right? You would get 1. That's right. So that's a reciprocal identity. So wherever you see sine x times cosecant x, you can put what in its place? 1. What about another one? Tangent times cotangent. All right, John, you ready to give me the other one?
Yeah. Cosine times
Cosine x times secant x, yes. Are you noticing wonderful things are happening all over the place?
a lot of ones.
A lot of ones. Nice, right?
Yes.
We like it when we can replace the trig functions with 1. Now, there are some corollaries, I call them, from the Pythagorean identities that we can derive. So let's say I take the big one here, this cosine squared x plus sine squared x equals 1, and I want to figure out what sine squared x equals. What could I do to this equation? That's right, so it's going to be sine squared x equals 1 minus cosine squared x. Everybody follow that? All I did was subtract cosine squared x from both sides. Similarly, what could I do with cosine squared x if I wanted to solve for it? What's that going to equal? That's right, so it would be 1 minus sine squared x. Yep.
Sorry, can you explain one more time?
Sure. Okay, so I'm taking the cosine squared x plus sine squared x equals 1, and I'm going to solve for this first one, sine squared. So how do I get it all by itself?
Subtract cosine squared x
From both sides. These cancel, right?
Oh, so I understand. Okay.
Yeah, that's all right. Sometimes we just have to.
Yeah, my head was down. So.
No, that's perfectly fine. So that's where it comes from. Yep.
I don't understand the reciprocal identities.
Reciprocal identities up here.
Yeah.
Remember when we did, we said sine of theta was equal to the opposite, right, over the hypotenuse? Oops, if I can write. And cosecant is what? The hypotenuse over the opposite, right? We defined cosecant to be the reciprocal of it. That means if I were to multiply the sine ratio, which is opposite over hypotenuse, times the hypotenuse over the opposite, what happens? It equals 1. So that's what's going on. Does that make sense? And the same thing with tangent. This would be sine over cosine times cosine over sine, and that equals 1.
Okay.
Cosine would be adjacent over hypotenuse times hypotenuse over adjacent, that equals 1. Okay? That's great. Now, why do we care about this? If you look at 1 minus cosine squared x, is this the difference of perfect squares? Yes, isn't it? Because you could factor this. You could say 1 plus cosine x, 1, right? So I'm just throwing that out there. What about 1 minus sine squared x? Is that perfect square? Yeah. All right, so let's go back to the first page. Going back to the first page. And we're going to look at number 5 now, because that's going to have some meaning to us. You see anything?
1 minus cosine.
Yes, let's look at that. 1 minus cosine squared x. Did we just discover that equals something? What does it equal?
Sine.
Sine squared x. So I can replace that using an identity, right? Because they are equal. We can say then that sine x in the numerator times 1 plus cosine x over sine squared x. Now, do we have 2 factors in the numerator?
Yes.
We do. May we cancel?
Yes.
We may. So we're going to get rid of one of these and 1 in the denominator, and I'm left with 1 plus cosine x over sine x. Now that you could argue is not as simple. This is probably similar in complexity here. But you could bust this fraction up on number 5 and say that this is 1 over sine x plus cosine x over sine x, which is equal to 1 over sine x is, what's the reciprocal? Cosecant plus cotangent. And I would argue that is simpler because if you think about it, what is the trig function? It's the ratio of sides, right? So let's say that the sine is 3/5 and the cosine is 4/5. Do you want to do this addition where you have 3/5 over 1 minus 4/5, or would you rather add the cosecant, which would be 5/3 plus, you just do one addition with fractions versus double-decker fractions? Do you see how this would be a simpler calculation? Yes.
Could we have done the same thing where we separated the 2 fractions on the top with the original problem?
No, why? That's a great question. Why? Because these in the denominator are separated by a minus sign. So you can't divide this in. You have to divide the entire thing into sine x, right? You can't split up that algebraically. Okay. So do you see how these identities will help us come up with simpler trig expressions? All right, so using one of the Pythagorean identities above that we solved for here, the 1 plus tan squared x equals secant squared x. John, why don't you help me and tell me what tangent squared is equal to? Tangent squared x.
It's equal to secant squared x minus 1.
Do you see that? You're just adding, subtracting the 1. Everybody see what happened? Is that the difference of perfect squares?
Yes.
All over the place. They're just popping up. And then what does 1 equal using this expression? This equation up here. Secant squared x.
Minus.
That's right. Secant squared x minus tangent squared x. And wherever you see this expression on the right, you can replace it with the number 1. That's nice. Moving along, the other forms of the identity here. What about the cotangent? Squared x plus 1 equals cosecant x. Can we rewrite it and figure out what cotangent equals? Yep, cosecant squared x minus 1. Perfect. And what does 1 equal? Cosecant squared x minus cotangent squared x. Very nice. So this piece of paper is going to be very, very important to you, I suspect. Now, these are cofunction identities. These are not on your sheet, and I'm going to go over them in the next unit. Okay, so this isn't going to be on a test or anything. All right, so where are we? Let's practice?
Yes.
So let's practice. And what we're going to do with 1 through 5 here is we're going to try to simplify the expression to one of these, an A through E, right? So we got to do something. So sine x times secant x. Is there anything I can change? That?
You can put secant x into one of the cosine x.
Right, so we'll say sine x times 1 over cosine x. I like that. And this is really over 1, isn't it? And that's sine x over cosine x, which is easily tangent x. So you see how this is E? Now the second one here almost looks like one of the ones we had in the previous,
Yeah, it's not.
except what?
Very far.
So what does that mean? Instead of 1, it's equal to negative 1. Brilliant. And so this is B. So if one of those identities is flipped, meaning the signs are the opposite, then you can make them equal to negative 1 instead of 1. Very nice. What about number 3? What can I change? Renee? Good. And then what is cosecant? Can we change that one too? 1 over sine x. Uh-oh, something nice is about to happen. We can cancel. Everybody see we can cancel the signs? And then I get 1 over cosine x, which is secant x. Very nice. So this one is A.
So A for secant x.
Yay, secant x, yes. All right, number 4. Something's jumping out at you, isn't it? I hope.
Yeah.
What is 1 minus cosine squared? X. Sine squared x. Very nice. This is sine squared x times 1 over sine x, right? And this sine squared is really over 1. which is D. See, these are kind of fun. Oh, wow, secant x times cosine x.
Oh, that's one.
That's 1 because they're reciprocals of each other. Very nice. So that's 1, and obviously that's C. Alright, so let's keep going. Rewrite the following trig expressions by using algebra and one or more of the trig identities. So I have cosine x plus tan x times sine x. Alright.
No idea what to do. So if you have to divide by sine x.
I would change. See, how many trig functions do I have in this expression? I have 3, right?
Yeah.
And there's only one I can change to make it 2 trig functions, right?
Oh.
Right? Because I can say here that cosine x plus sine x over cosine x times what? Sine x over 1, and now I'm down to how many trig functions? I've gone from 3 trig functions now to 2, so that's better.
Yeah.
And so now I have cosine x plus sine squared x over cosine x. But I don't know if it's any simpler, an expression, but now yep, what can you do?
Or got it under the common denominator.
Common denominator, you're right, so what would it be?
Cosine squared x plus sine squared x.
He's doing it all in one step. He's saying cosine x is my common denominator, and I'm going to multiply this first one by, so I'm going to get cosine squared x plus sine squared x. Anybody doing the happy dance?
I like
You know, the Snoopy dance, the Snoopy, you know, he's so happy.
iron.
Right? So the happy dance, why? Because what's the numerator now? 1. Something wonderful just happened. You guys aren't buying into the wonderful thing yet?
I'm buying.
Good. Because I can replace this with 1.
And then
1 over cosine x is secant x. Very nice. And that is certainly a lot simpler than what we started with.
Yeah, it is.
Did you get the denominator thing?
I think I messed up.
What are we multiplying this cosine by? And I know I don't have a lot of space here. I'm multiplying it by cosine x over cosine x, right? Which is cosine squared x over, see? All right. Number 2, I think, is easier. What do you think about number 2? What can we change? Denominator into? So this is going to be sine x times cosine x over cosine squared x. And now what can we do? Cancel. 1 in the numerator and 1 in the denominator. So this is sine x over cosine x, which is tan x. Now, I know that you don't have these last 2 on your sheet, so if you'd write them down, that would be great, because I think these are fun to do. I think you might have some space right here in the upper left. So let's do secant squared x minus 1 over secant x plus 1. You know, you have some. And on the back page, you know, where you have the 4 equations, you probably have space halfway down. You can do it there too. All right, well, what about this one? How many trig functions do I have? I just have 1. So I would resist changing it. But the denominator is going to give us a clue as to what we can do. Yeah, Renee? You could, John?
Multiply by secant x minus 1 over secant.
Could you do like the difference of squares?
What about the difference of squares on top? Can you factor the top?
Yeah.
Mary, that's a brilliant stroke. Yes, you can factor the top. You see that? Is that the difference of squares? So what can we do? We can say the top is going to be secant x plus 1 times secant x minus 1. It doesn't matter if you put the plus or the minus first. You know, it's multiplication. Over secant x plus 1, and then cancel the secant x plus 1 and the secant x plus 1 in the denominator, and we get secant x minus 1. Yes, John?
Do you want to say that's tan squared x or no? Does that make it more complex?
You see, that's what I was trying to allude to. Is that you see these are the same trig function. I wouldn't introduce a second one if I didn't, if I could resist it. Now, what I would do before I changed it to tangent, I would change this to 1 over cosine squared, and this would be 1 over cosine. And then you have double-decker fractions, and you would want to pull your hair out probably.
Yeah.
But I just want you to think that maybe you could factor it, and things will go better. What about number 4 here? It's 1 over 1 plus cosine x plus 1 over 1 minus cosine x. Common denominator, I like it. Let's see what happens when we do that. The denominator is going to be pretty big. It's going to be 1 plus cosine x times 1 minus cosine x. And the numerator is going to be, what do I multiply this first fraction by? Good. 1 minus cosine x plus, and then I multiply this fraction times 1 plus cosine x. Now, I don't have to worry about distributing anything right here because it's a plus sign. If this was negative, I'd put this in parentheses so I'd make sure I distribute it properly. But it's not. We don't have to worry about that. What happens in the numerator?
The cosines cancel out.
They do. And then how many am I left with on top?
Just have 2.
It's a 2. What can I do on the bottom? John?
It would be cosine squared x plus 1 minus 1.
Or 1 minus?
Sorry, 1 minus cosine
Yes,
squared.
it would. It'd be 1 minus cosine squared x. And then,
Sine squared.
that's sine squared, right? So that would be 2 over sine squared x. But what's 1 over sine squared?
That's
Cos squared
So it's 2. So this is going to be equal to 2 cosecant squared x.
Wait, how did you...
Okay, this I could break this up as to 2 over 1 times 1 over sine squared, right? Could I do that mathematically?
Yes.
Yeah.
So this would be 2 times cosecant squared.
Oh, alright.
I would like you to get to the point where you can see this step right here, but this is what I'm doing.
Alright.
Okay? You follow?
Yeah.
Look at all this algebra we're doing with trig functions. Pretty fun. Pretty amazing, yes?
So do we just have to memorize all this?
Yes. So let's talk about it. Well, the first one we had memorized, the first Pythagorean identity, what's that? Cosine squared
Plus sine squared.
equals 1. And then can you derive the other two pretty quickly?
Yeah.
By dividing by cosine squared x, and then sine squared x, and then you can add and subtract and get all sorts of other fun identities. What you guys don't realize is that you're going to have these down very quickly because you're going to be hunting for them. You're going to be like, I wish that was 1 minus cosine squared on the bottom so I could change it to sine squared. You'll be thinking like that. And this is new, so you're not thinking that yet. But you'll get there. Okay? So, the last thing I want to do is do some more complex solving equations. Alright? So I'm on the back now. And we're going to solve the following equations between 0 and 2 pi, which means our brain is in what mode? Radians. And we are going to isolate the trig function. That means we're going to get the trig function on one side by itself. So what am I going to do here for number 1? Add a sine x to the other side. So I'm going to go plus sine x. And I know you guys are in honors pre-cal, but I'm going to show you these steps on this one first, right? And then I'm going to do what? Subtract root 2. So we're going to get, how many sine x's on the left? Yeah, very nice. So 2 sine x equals, negative root 2. Divide by 2. Yes, Haley, you're right. Divide by 2. So we get sine x equals negative
Root 2 over 2.
root 2 over 2, which I hear in your voices. An aha moment, that's one we know, isn't it?
Yes.
So we have to decide what quadrants the sign is. Negative, which is 3 and 4. Draw our reference triangles. We know we have two solutions. What's alpha here? Where in the first quadrant is pi over 4. Very nice. You guys are finishing my sentences before I get them out. That's a good sign. So what is theta 1 here? Or x1, I should say, because my variable is x. That's good. X is 5 pi over 4 because it's the quadrant 3 pi over 4 angle. Quadrant 4 pi over 4 angle is 7 pi over 4. Look at that. You did your first more complex equation. All right, so let's hop to number 2. That's looking trinomial-like.
Oh, so you factor it.
We factor it. Yes, ma'am.
So sine.
2 sine x and then sine x, right? Now what?
2 sin x gets a minus 1 sin x.
Say it again? He's beating you out there today.
Yeah,
What
it's okay.
what is it going to be?
2 sin x gets a minus 1.
The 2 is minus, right? So it's going to be here, and this will be plus,
Oh, yeah.
right? Now, I'm going to use something called the zero product property, right? When you multiply two things together and they equal 0, what has to be true?
Each one equals 0.
One of them has to be 0, right? So we're going to say 2 sine x plus 1 will equal 0, or sine x minus 1 equals 0. So now we have two basic trig equations again. I'm going to isolate the trig function, so I'm going to subtract 1 and then divide by 2. So you get 2 sine x equals negative 1 sine x equals negative 1/2, and we are in still what quadrants here? 3 and 4. And so alpha here, where in the first quadrant is the sine 1/2? Pi over 6. Very nice. Right, I'm doing the hand thing. You guys didn't see me. I was taught secretly doing it behind my back, so I would know. So x1 here is 7 pi over 6, and then x2 is 11 pi over 6. Nice. But I'm not done yet. God bless you. God bless you again.
Thank you.
Sine x equals 1. Where does that happen? That's quadrantal-like. Sine is the y, right?
Oh, so it's either pi over 2 or 3 pi over 6.
Up here, but it's just 1, right?
Oh, so it's
So it's,
3 pi
right,
over
so
6.
it's there. So it's going to be x equals pi over 2. That's the only solution we get from that factor.
Shouldn't one of the answers be extraneous?
No, why? Because there's 2, but there's more than 2. Because when you have a quadratic, how many are you supposed to have? 2 answers. You have 2 real zeros, right? However, the trig functions, yeah. So for some, yeah, because you can have multiple. So it's a little bit different, isn't it, than a polynomial? That's great. I like the fact that you're thinking about that. Uh-oh. Number 3. What do we do here? Factor out a cotangent. I like it. Cotangent of x, and what's left? Cotangent squared x minus 3 equals 0. I'm going to use the zero product property. So we can say cotangent of equals 0, or cotangent squared x equals 3. I'm taking the liberty of moving that 3 over really fast. Is that okay?
Yeah.
Now, I don't like to deal with cotangent. Do you? We only memorize the tangent once.
Yeah.
So I'm going to reciprocate this. So what happens when you reciprocate 0? Undefined. Very good. So that's where the tangent is undefined. And then this is going to be tangent squared x equals 1/3. Very nice. So where is the tangent undefined? On the unit circle?
Yes.
On the y-axis, right? So we have two angles here for an answer, which are x equals
80 degrees.
pi over 2. We're in radian mode, right?
Yep.
And then
3
3 pi over 2. Very nice. And my domain was restricted from 0 to 2 pi, so we want the positive ones only one time around. Tangent squared x equals 1/3. Tangent x equals, whoops, tax. Tangent
1/3. Yeah, 1/3. Sorry.
plus or minus, right? When you take the square root, you've got to take into account the positive and the negative roots. So that's going to be the square root of 1/3. So tan x equals plus or minus, this is going to be, what's the square root of 1?
1.
So this is 1 over root 3, which is root 3 over 3, good. But it's plus or minus. So what quadrants is the tangent? All of them. Very nice. So we have to draw the entire bow tie, don't we? Of reference triangles. So how many answers do we have in one go round? 4. So what is alpha? Where in the first quadrant is the tangent root 3 over 3?
Pi over 6.
Good. Pi over 6. And so then we can say x1 is going to be pi over 6. x2, 5 pi over 6. x3, 7 pi over 6. And then x4, 11 pi over 6. Wow, we got 4 answers from this factor.
Is there any way to tell how many answers you'll get?
Well, when you're in all 4 quadrants, if it's plus or minus, you're going to get 4.
Oh, I
If the quadrantal is equal to undefined or 0, you're going to get 2. If it's equal to 1, you're probably going to get, if a quadrantal is equal to 1, you're going to get 1 angle. And then, but I don't want you to memorize it. Just, if you draw the reference triangles, you'll be okay. It works out for you. So now, we're going to go to number 4, which I've thrown a monkey wrench into because it's 2 sine squared x plus 3 cosine x minus 3 equals 0. Can we factor them?
Yeah, well, no, but
No, why?
because it's not the same.
They're 2 different trig functions. So what can we do? Yes, Renee?
You can replace sine squared x with 1 minus cosine.
Yes. So you cannot factor anything because guess what? This is different. But I have a Pythagorean identity that can help me out. So I can go 2 times 1 minus cosine squared x because I know sine squared x is equal to that, right? And change them all to the same trig function. Everybody see that? There's a little bit of magic that I just did. And now we're going to distribute. So we're going to get 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And I'm going to rearrange these things and get negative 2 cosine squared x plus 3 cosine x. And then if we do 2 minus 3, we get minus 1. Now, I don't like to factor or do anything with a negative in front.
Yeah.
So I'm going to factor out a negative, leave it hanging outside there, and go 2 cosine squared x minus 3 cosine x plus 1 equals 0. Now, does that factor?
Yeah.
It does indeed. What would we do if it didn't factor?
Quadrat.
But that's the next unit. Yeah. Did you see what I did?
Oh, yeah. I figured it out.
Okay.
I was gonna say it's
Yeah. So what happens? What are my factors here?
2 cosine x minus 1 cosine x minus 2.
Cosine x minus 1. This problem is impinging on the other one, isn't it? This one right here. All right, so I have the 0 product property. Will negative 1 ever be 0? The factor out here? So I don't have to worry about it, do I? So we're going to have two equations. 2 cosine x minus 1 equals 0, or cosine x equals 1. I'm going to take a liberty of doing that really quick solving for it. So let's do the 2 cosine x equals 1. Cosine x equals 1/2. What quadrants is the cosine positive? 1 and 4. So what's alpha here? Pi over 3, good. So x1 is going to be pi over 3. x2 is going to be the pi over 3 angle in quadrant 4. 5 pi over 3. Good. Cosine x equals 1. Where does that happen? At 0 or 2 pi, but what does my interval say at the top of the page?
Can't be greater than 2 pi.
So it's not, it equals on the 2 pi, right?
That'd be less than.
That's right. So it's just going to be x equals 0. All right.